Hello, welcome to this video. In this session, we are going to talk about ARM architecture. If you are electrical or computer science engineer, you must be aware about Intel architectures or Motorola MPC86 series architecture. Here I will give little emphasis how ARM architectures different from other and how it save power. The unique feature which ARM architecture got is low power. We call it low power architecture also, and that is the basic reason this architecture is there everywhere in core. It's not there only inside, it is there everywhere. Let's start this. The ARM architecture. In this presentations I will cover basically 4 topics. First, I will introduce ARM as a company. I'll give you a little bit background to who ARM Limited are, what we do, and how our business model works. Then I will cover program models and ARM architectures. In program models, I will give you a little bit insight about the structure of the ARM architecture, how it has developed, register set, models and exceptions, and then Indian issues. Little Indians and big Indians. And then give you a little bit insight about the instruction set, overview of the features of the ARM instruction set, the coprocessor mechanism, and the overview of Thumb, why it has designed and the benefit it gives and what benefit it gives. And then I will jump into the system design. We'll give you a little bit overview of some of the hardware and software technologies that ARM has to support the design in the ARM core into the real product. Also, I will look at some of the issues involved in the memory map in the ARM based system, and then I will touch upon the development tools. ARM Limited. The ARM processor core originates within British computer company called Acorn. In mid 1980, they were looking for replacement for the 6502 processor used in their BBC computer range, which were widely used in UK school. None of the 16-bit architectures become available at that time to meet their requirements. So they designed their own 32-bit processor. Other companies become interested in this processor, including Apple, who were looking for the processor for their PDA project, which became the Newton. After much discussion, this led to Acorn processor design team is splitting off from Acorn to the end of 1990 to become Advanced RISC Machine Limited, now just ARM Limited. Thus ARM Limited now design ARM family of RISC processor cores together with range of other supporting technologies. One important point about ARM is that it does not fabricate silicon itself, but instead just produces the design. We are in an intellectual property business, IP business. We are IP company. Instead, silicon is produced by the company who license the ARM processor design. This is a little bit history about ARM Limited. Also, we develop technology to assist with the design in of the ARM architecture. Software tool like board, debug hardware, application software, bus architecture, peripherals. Also, ARM as a company has developed hard IP also. Hard IP means in any chip, any semiconductors chip, you will have very tiny cell, like in human body, right? We have a cell. Similarly, in any chip, we have very tiny cell of nanometer square area, small cell. That cell also designed by ARM, and that cell called standard cell, and other part of it is called memory and IOs. These all together called physical IP, and this IP is also developed by ARM, and most of the companies uses ARM physical IP. Means if you have any semiconductor devices, it's a 99% chances that you will have the cell inside which was developed by ARM Limited. This is the little bit introductions about the ARM. How does this ARM came about and what it does. Okay, now let's see ARM activities. This slide helps explain where ARM product plays. A generic digital product. This is a generic digital product. ARM supplies a system level IP into the SoC along with the physical IP. This one you are seeing right here. This is a small tiny cell. These are the physical IP which is provided by ARM to ensure it's manufacturable. We ensure like this tiny cell would be manufacturable. We provide software IP into the system, development tool to help design and build the system architecture and software. And finally, we work with an extensive third-party community to make the whole device creation possible. Remember, this helps frame what we do not cover also, right? Industrial design of the device, like industrial design of the device. These are the list of ARM connected community. More than 700, and it's growing. Means one way or other, directly or indirectly, these are the company which are connected through ARM, through physical IP or through ARM core or through software, whatever. These are the full community which is connected through ARM. And then you must be wondering, what are those companies creates and where ARM processor go into, and then I would say, yeah, it is here, huge range of applications. Means everywhere in all of these equipment you will find ARM processor and ARM physical IP also. If you see this, how many ARM do you have at your home? You have cell phone, ARM is there inside. You have a disk drive, ARM is there inside. Means almost 100% of the cell has ARM processor inside and physical IP too. And approximately 70% of disk drive have ARM code in it. A smartphone, similarly mobile computers, digital TV, microcontrollers, cars, and PC peripheral. See, huge opportunity for ARM technology. In 1998, very few, and then it developed to become 20 billion plus core, and it's targeting to make it 100 plus billion. It would be more. This is just target. Why it is so popular? Because of unique architectures we have in ARM which save power, and this is what we are going to discuss today. If you see Nokia N95 multimedia computer, what you will see here, this is a very good example of an ARM based product. The idea again is that there are a number of different companies involved in something like this, with ARM being at the core of the product as well as other places too. For example, a Magma EDA tool used for chip development, for example synthesis, place and route, circuit simulation, verification, etc. S60 is a multi-vendor standardized software platform for mobile phone for Nokia that run on Symbian. It consists mainly of a suite of libraries and application for doing things like telephony and multimedia. So Nokia licenses this OEM like LG and Samsung. In this way, ARM directly or indirectly connected through all kind of low power devices. What's happening in microcontrollers? See, microcontrollers are getting cheap. Can you imagine 32-bit ARM Cortex M3 microcontrollers just for $1? So in today's age, we are seeing more cost efficient, faster, more inclusive and more power efficient microcontroller going into sort of devices. These days you can get low end controller for less than $1 also, and at higher end one based on M3 for approximately $1. On a single chip you get lot of memories, IOs and variety of other peripheral and connectivities. In effect, all of this creates this new opportunity for MCU, where now you see all sort of devices with MCU and didn't previously have them. For example, shoes and clothing, things around your kitchen like toaster, microwave, and even toilets in your bathroom. This all will have some or other kind of microcontrollers, ARM microcontrollers. See here, world's smallest ARM computers. World's smallest perpetual solar powered sensor network at about 1 cubic millimeter in size for use in biomedical plant, so that it could harvest energy by motions or by heat instead of light, or maybe build a bridge monitoring. The average power consumptions of this processor is under nanowatt. It means 1 billionth of watt. 1 billionth of watt. Not an off the shelf part, but they go for under $1. So this is 1 cent. If you are India, you might have seen that 25 paise, the coin of 25 paise, the size this 1 cent would be equivalent to 25 paise coin. And then see how small this processor is, and this generally go into into the plants and all biomedical things. Now, world largest ARM computer. Neutrino. You must be knowing about neutrino. Neutrino is a particles. Is similar to electron, but have no electric charge and come from nuclear reactions from the sun, arc from dark matter. The system acts as a telescope to detect dark matter like supernovas and black holes in the universe. The detector is about the size of a basketball. The here is like full of this processor. Approximately 42,000 ARM powered neutrino detectors are used here, and it get activated whenever it will see any of the neutrino hitting anywhere there, and based on that it will do some analysis and some processing, and then it will give a result at the output. It means see the range, see the size of the computers here. It's ranging from 1 millimeter cube to 1 kilometer cube. Means it's covering whole range. Here we have some video, but at this moment I cannot play this video. This video is not for public, it is for internal. I'm sorry for that. Let's jump into the another part. This is the end of the agenda, end of the introductions that we have about ARM. Now you might be knowing what ARM is, what we do and all. Now I'm going to cover about ARM architectures and program model. Here I will discuss like the structure of the ARM architecture, how it has developed, register set, models and exceptions, and the Indian issues. If I'll get time, I'll cover this. ARM classic processor portfolio. You will see here version, and it's very confusing. You have to be very careful here. ARM version 4, ARM version 5 and ARM version 6. These are the architecture. You can say architectures are instruction set. Program model. This ARM develops instruction set architecture, for example program models, then processor design that execute ISA. See, we have another version also, ARM version V1, which is obsolete now. Version V1, V2 and V3 are obsolete, and mostly used ARM architecture instruction set is ARM 4. It has got ARM 7TDMI. Most of the university teaches this, but after that lot of development happened, and we are here in ARM version 6. After ARM version 6, what happened when we went into ARM 7, that we changed the name of that ARM version 7. We call it ARM Cortex, means simply Cortex processor. The ARM Cortex A family is a version 7A, and this one is specifically designed for applications processor, for full operating system and third-party applications. Cortex A. It means it has version 7A architectures and instruction set. Another category of Cortex is ARM Cortex R family, which has got V7R architectures and instruction set. It is used for embedded processor, for real-time signal processing, control applications, mostly in medical equipment. Then third family is ARM Cortex-M family, V7M. This is the microcontroller oriented processor for MCU and SoC applications. This Cortex has three versions, A, R and M. Depending on the usage and all, that core can be used. It's clear? It's very important. Version 7 instruction set and architectures, very popular, and that is called Cortex. So version 7 of the instruction set architecture coincides with the introduction of the Cortex product naming conventions. Wherever you will see Cortex, it means it's the ARM version 7 architectures. The Cortex processors are named based on how they are used, along with the qualitative numeric indicators of the performance and functionality. So we have shown these three families here. So hardware virtualization is when the virtual machine manager is embedded in the circuit of hardware component instead of being called up from third-party software applications. The virtual machine manager is called hypervisor. The job of hypervisor is to control processor, memory and other firmware resources. The hypervisor acts like a traffic cops, allowing multiple operating system to run on the same device without requiring source code or binary changes. Each operating system appears to have the processor, memory and the firmware resources all of itself, but in reality the hypervisor is controlling the processor and its resources, allocating what is needed to each operating system in turn. The hardware virtualization is an evolving technology that may become dominant, especially for server platform, because it has potential to facilitate consolidations of multiple workload on a single physical server without requiring third-party software. This slide gives you a little bit idea about the performance, relative performance between different ARM version, different ARM core, I could say. Like, see, from Cortex M0 to Cortex A9 dual core. These are this y-axis, the maximum frequency, megahertz in megahertz, and this one says the minimum power, milliwatt per megahertz. If you see from here to here, speed got increased tremendously, and power little bit, but power is in under control. Means this Cortex A9 dual core with frequency approximately 2000 megahertz, means 2 gigahertz, and it take power approximately 0.5 milliwatt per megahertz. Isn't it amazing? And but this number will change depending on your technology, your core technology, device technology. 130, if you have 130, it will vary from 130 to 45. Okay, this is just a relative number, relative yeah, it's a relative number, it's not absolute. Cortex family, that is the most important things. Cortex family, Cortex A8 that we discussed just now. Cortex A8 means Cortex A8, Cortex means version 7, then version 7 and then A8 is a core. Cortex R4, Cortex M3. So what are things are there inside Cortex 8, and what are things are there in Cortex R4, and what are things are there in Cortex M3. So A means application based here, and here R is real time, and M is a microcontroller. This is a microcontroller. Yeah, let's see what Wikipedia tell us about this processor. Time to time I will go through Wikipedia or sometime in ARM website to give you a little bit more insight, so that later on you can browse through those links and get much more idea about it. So see, ARM Cortex 8 in Wikipedia, it says Cortex A8 is a processor core designed by ARM Holding, implementing the ARM v7 instruction set architecture. Compared to ARM 11 core, the Cortex A8 is dual issue superscalar, achieving roughly twice the instruction execution per clock cycle. And some of the features is given here. And key features of Cortex A8 core are frequency from 600 MHz to 1 GHz and above, superscalar dual issue micro architectures, Neon SIMD instruction set extensions, this is optional, VFP version 3 floating point unit, this is also an option, and it runs on Thumb 2 instruction set encoding. I will give you a detail about it. There is ARM instruction set, Thumb instruction set, and Thumb 2 instruction set. It has the features of JZIL RCT. If you want to know little bit more about it, you can just browse through these all link. You'll get more idea. Advanced branch in predictions unit with 95% of accuracy, integrated level 2 cache up to 4 megabit, and 2.0 DM IPS per megahertz. Implementation, these are the feature where it implemented. See, you will be amazed to see that. Several system on chip have implemented the Cortex A8 core, including Apple A4, Freescale IMX51, Samsung Hummingbird, TI OMAP 3. Similarly, we have Cortex R4 and Cortex M3. Cortex R4 is for real-time applications. If you want to know more about this, here Cortex M series. If you want to know Cortex R series and R4 processor, so here you are, R4 processor. The Cortex R4 processor is the first deeply embedded real-time processor to be based on ARM version 7 architecture. It is intended for use in high volume, deeply embedded system on chip. Applications such as hard disk driver control, wireless baseband processor, consumer product, and electronic control unit for automotive system. Cortex R4 delivered substantially higher performance in real-time responses and more feature than other processor in its class. This processor offers excellent energy efficiency and cost effectiveness for ASIC, ASSP, and MCU embedded applications. Furthermore, the Cortex R4 processor can be configured at synthesis time to optimize its feature set for a precise match with the application requirement. That is the beauty of Cortex R4 processor. Similarly, if you want to know more about Cortex M, you can browse through simply and get to know about it. Cortex M3. It is also based on ARM version 7 architecture. Cortex M3. See, the ARM Cortex M3 processor is the industry lead 32-bit processor for higher deterministic real-time application, and has been specifically developed to enable partner to develop high performance low cost platform for broad range of devices including microcontroller, automotive body system, industrial control system, wireless networking and sensors. The processor delivers outstanding computational performance and exceptional system response to the event while meeting the changes of low dynamic and static power constraint. The processor is highly configurable, enable a wide range of implementation from those requiring memory protections and powerful trace technology through to extremely cost sensitive device requiring minimal area. This is the Cortex M3 processor. So these are all about Cortex family A8, R4, M3. Data size and instruction set. Here, just not to confuse you, first I will give some statement I'll define something so that bit, byte, half bit, word should not confuse you a lot. So here in ARM, word, which will mean is 16-bit, okay, but in ARM in general 16-bit means one word, right? But in ARM word 16 bits is a half word. Why? Because our architecture is based on 32-bit. Our word means 32-bit. If we call one word will have 32-bit and half word will have 16 bits. It is totally different than other processor, where for other processor we say one word means 16-bit, half means 8-bit, but in terms of ARM, because ARM is started with 32, one word is 32-bit, simply half word is 16-bit. Java bytecode are 8-bit instruction design to be architectures independent. Jazz transparently execute most bytecode in hardware and most in highly optimized ARM code. This is due to trade-off between hardware complexity, power consumption, silicon area and speed. So ARM is a 32-bit architecture, very clear. When we use relation to ARM, word means 32-bit, byte means 8-bit as usual, half word means 16-bit, means 2 byte, and word means 32-bit. Most ARM implement two instruction set, 32-bit ARM instruction and 16-bit thumb instruction set. So we have two kind of instruction set. One is 32-bit instruction set, which we call ARM instruction set, and 16-bit we call thumb instruction set. There's one more instruction set which is a mix of these 32 and 16. We call thumb 2 instruction set. Jazz cores can also execute Java bytecode. Here's a little comparison between ARM instruction set and thumb instruction set. Initially, in the beginning, ARM instruction set was written. After that, another instruction set called Thumb is written, and then Thumb 2. What's the difference between these two, and how we can compare the performance and power between these two operation code? The intention of this diagram, or you can say a comparison, is to show a comparison of memory usage between ARM and Thumb instruction when running from different size memory width. When this one is running with 32-bit memory width, then what is the comparison like? When it's running with 16-bit memory width, what is the comparison like? When it's running with 16-bit and 32-bit stack, then what is the usage like? So see, in 16-bit memory, if you see, Thumb code is better. You can see here, in 16-bit memory, Thumb code is better. It gives good performance. Even though there are more instructions, each instruction only takes single cycle to fetch, whereas ARM instruction will take 2 cycle, because this is 16-bit memory, and for ARM instruction it requires 32-bit. For every fetch it will take 2 cycle, and that's the reason if you have 16-bit memory, Thumb will give good performance than ARM instruction set. However, you can see in the 16-bit example that the performance from Thumb goes down. For Thumb, performance of Thumb in 32 performance of Thumb goes down. Despite it still takes single cycle to fetch each instruction. This is because data access, and it particularly stack access. Even in Thumb, each access to the stack will be 32-bit quantity, as a register contain or transfer, and this lowers the performance on full 16-bit memory architecture. One way around this is to provide a limited amount of 32-bit memory to place you stack in, which can give you a useful performance boost. In this case, the boost gets performance almost back to the full 32-bit performance level. The difference is due to dry stone benchmark using integer 32-bit global data, which is still being stored in 16-bit memory. So if you have like 32-bit memory width, obviously ARM will give better performance. If you have 16, Thumb will give good performance. If you have like options for both 16-bit with 32-bit stack, then again Thumb will give better performance. Means here Thumb's performance would be approximately same as what we have here, right? Thumb's performance would be same, but this ARM performance will go down a little bit. The Thumb 2 instruction set. Cortex M3 implement only subset of Thumb 2 instruction set. It has some but not all. The variable length instructions, ARM instructions are ARM instructions are fixed length 32-bit. Thumb instructions are fixed length of 16-bit. Thumb 2 instructions can be either 16-bit or 32-bit. No restrictions there. In Thumb 2 gives approximately 26% improvement in code density over ARM, and Thumb 2 gives approximately 25% improvement in performance over Thumb. The overall Thumb 2 is better, and in all modern core processor we use Thumb 2 instruction set only. Cortex M3 programs model. The great thing of our program model is like it's fully programmable in C, programming C. So programmers no need to know like how ARM assembly would look like, and they don't need to write a program in ARM assembly code. They have to write simply in C code, and then compiler will convert that C program to ARM assembly program. And a compiler will generate all opcode and everything based on your C programming. This is stack based programmer and exceptions model, more analogous to traditional 8 and 16-bit architecture. So it's aimed at designer coming from that background. The stack based means PC means program counters, PSR, LR, and corruptible registers automatically push into the stack upon exceptions in hardware, as opposed to manually doing it in software for other ARM processor. Vector table contain address that are fetched upon accepting interrupt as opposed to the instructions. The two model means less initializations. First beautiful thing is like fully programmable in C, and this is stack based exceptions model. Only two processor modes we have here: thread mode for user task, handler mode for operating system task and exceptions. And vector table contains address. This is how the whole ARM means outlook of ARM processor. It's like if it will work in the two mode. One is like privilege mode, another is non-privilege mode, and this is basically based on M3, Cortex M3, and it supports two operating modes. First it called thread mode, and then handler mode, which can be thought of as dividing the system into supervisor and a user mode. These are actually the term used for the modes on ARM processor. Further, the M3 supports two-level access for code, privilege and unprivileged. The two-level access for code enable the implementation of complex open system without sacrificing security of the applications. Unprivileged code limits or excludes access to some resources such as specific instructions or memory locations. So the user side, where most application code runs, and support non-privileged and privileged code. The supervisor side support only privileged code. Exceptional events such as operating system call, for example, to allocate memory or perform some other operating system task, or error conditions like undefined instructions, are the only way to go from the user side to the supervisor side. Other exceptions events are external and includes things like memory abort, interrupts, and resets. Finally, and again, the technical term for these two modes or operations are thread and handler. This is the technical term which we use in ARM. Thread mode means as a user mode, handler mode means supervisor mode. The two mode, thread and handler. Cortex M3 interrupt handling. Cortex M3 has NVIC, Nested Vector Interrupt Controller, a kind of peripheral to support up to 255 interrupts. Other than that, it also has WIC, Wake Up Interrupt Controller, which is similar to NVIC, but it doesn't need any clock to run. Hence, it can be used to detect any interrupt during sleep mode without burning energy. That is the beauty here, to save power. No need to have any clock running inside the system for WIC interrupt. Since WIC is only available on revision 2 of Cortex M3, I'm not going to discuss about this in this presentation. Basically, from top level, if you see the interrupt and exceptions, these are divided into two categories: configurable priorities versus unconfigurable priorities. On Cortex M3, the exceptions and interrupts are divided into two categories based on their priorities, actually: configurable, unconfigurable. The unconfigurable priority interrupts have fixed priority and consist of 3 interrupts. Okay, unconfigurable priority that would not be configured. Actually, it has a fixed priority and consists of 3 interrupts. First, reset, invoked on power on and reset. Non-maskable interrupt, NMI, an external interrupt activated by external pin that is unstoppable except by reset. Hard fault, any fault that is not handled by other fault handler, means memory management fault, bus fault, usage fault, will activate this interrupt. The interrupt is also activated when the other fault handler are turned off. So these 3 exceptions are unconfigurable. Those interrupts, exceptions, are the basic interrupts that expected to be handled by applications, and it must be implemented by applications. The priorities is started at -3 for reset, -2 for NMI, and -1 for hard fault. The rest of 252 interrupts are configurable, starting from 0, the highest priority, until 252, the lowest priority. Global interrupts and enable disable. During initial reset, NVIC is turned off. Therefore, processor cannot receive any interrupt except for NMI, reset interrupt, and hard fault. To turn on interrupt with configurable priority, we write a code like ASM volatile CPSI 1. The CPSI is assembly instruction to enable the priority configuration interrupt. Actually, it is a shortcut to this longer procedure. If you want to see the how this code would look like, I'll take you to this one. See, global interrupt, enable, disable. This is how your program would look like, means exceptions, configure code. To turn off priority configurable interrupt, you put this. Are taking the longer non-atomic procedure, you write ASM volatile moves R0 H1 and then MSR PRI mask R0. Actually, if it is needed, the hard fault interrupt can be turned off as well, along with the priority configurable interrupt with this command. CPS IDF are using longer non-atomic procedures and so on and so forth. You can go through this this detail of all interrupts and exceptions. It is available in Google. Just search it, you will get it. So overall we have like reset, NMI and fault, hard fault, memory manage, bus fault, usage fault. Then we have SV call, privileged operating system request, debug monitor, debug monitoring program. Pend SV means pending SV call. Systic interrupt means system, internal system timer that is used by RTOS to periodically check resources or peripheral. Exceptional interrupt, that is external peripheral. Let's take a little break at this moment and then we'll start. Cortex M3 program status register. I'll be back in 1 minute. Just enjoy yourself. Welcome back. Cortex M3 program status register. Basically, we have three kind of status register. One is APSR, application program status register. This one, NZCVQ, IT and T. IPSR means IPSR, interrupt program status register, interrupt and exceptions. EPSR, executions program status register, which is this one. So we have kind of three categories of this status register. In EPSR we have IT field, if then field, ICI field, interruptible continuable instruction information, And then we have a combination of these three, which we call XPSR, which is combination of APSR, IPSR, or IEPSR, or AEPSR, like this. Let me show you. PSR is regular, this is read-write, and IEPSR means it's a combination of EPSR and IPSR. Similarly, IAPSR, APSR and IPSR. Similarly, EAPSR. Only IEPSR is read only, and other is read-write and read-write. The APSR means application program status register. It has bit n, 31st bit n for negative or less than flag. Means if it is 0, the operation result was positive, and if it is 1, operation result was negative. Means, got it? Bit 31 is n. If n is 1, operation result is negative. If n is 0, operation result is positive. Bit number 30 is Z, 0. If it is 0, operation result is not 0, and if it is 1, operation result is 1. Similarly, for carry, C, overflow, V, Q is for sticky saturations flag. If it is 0, indicate that saturation has not occurred since reset or since the bit was last cleared to 0. And bit 26 to 0 is kind of reserved. Similarly, for IPSR, interrupt program status register, it is from 0 to 8, means here. IPSR, this one. Okay, so if it is 0, it is from bit 0 to bit 8 approximately. So if it is 0, means thread node. If it is 1, it's reserved. For 2 for NMI, non-maskable interrupt. 3 for hard fault. 4 for memory management fault. 5 for bus fault. 6 usage fault. 7 reserve fault, and so on and so forth. Conditional execution and flags. What is that? Usual but powerful feature, conditional, of ARM instruction set. Other architecture normally only have conditional branches. Some recently added ARM instruction, like in version 5T and version 5TE, are not conditional though. Core compare condition field in instruction against NZCV flag to determine if instruction should be executed or not. See, ARM instruction can be made execute conditionally by post-fixing them with appropriate condition code field. This improves code density and performance by reducing the number of forward branch instructions. See, this is the usual one, and here this comparison R30 add an E. If not equal, then add it. Similarly here, compare is not equal, then skip. If equal, then add. So here I don't need this kind of branch here for conditional executions. So by default, data processing instruction do not affect the condition code flag, but the flag can be optionally set by using S. CMP does not need S. Okay, that's the advantage. You can see this code, right, of conditional execution code. Similarly, other if then means IT instructions added 16-bit. up to three additional then or else condition may be specified. Te we can put. Make up the for the following instruction like ITTET means what? See, the previous limitation of 16-bit thumb instruction was the inability to perform conditional execution. But in thumb 2, we have a new 16-bit if then means IT instruction for doing so. The 16-bit instruction looks like so. If it says equal condition or Z flag in PSR is true, then execute instruction 1, okay, and 2, else execute instruction 3 and then execute instruction 4. This is what it says. Any CC can be used, however 16-bit instruction inside the block cannot set flags with the exceptions of the comparison instructions. A special IT means if then status bit in PSR, so a block can be safely interrupted and returned to, otherwise the if then means IT condition wouldn't know whether this has happened or not, and you should not branch into or out of the block unless it is last instruction of the block. Again, the instruction would have no knowledge of the IT condition, if then condition, since PSR is not pushed and popped upon the branches. Classes of instructions. These are the classes: load, store, miscellaneous, some data operations, and change of flow. So here branch instructions. Branch instruction is like B condition and label, BL condition and subroutine label. This one is conditional field 31 to 28, and then link bit 0 branch. If it's 1, then 1 branch. The processor core shift the offset field left by 2 position, sign extend to it, add and add it to PC plus minus 32 byte range. How to perform longer branch then? Let's see in the next slide. We have a data processing instructions. Data processing instruction, we have like 4 types of it: arithmetic, logical, comparison and data movement. Okay, in arithmetic we have add operation, ADC, add conditional, subtract conditional, and RSB, RS conditional. Logical operation, AND operation, OR operation, EOR operation and BIC operation. Comparison, CMP, CMN, TST, TEQ. CMP is like subtract. CMN is like add. Subtract of the negative number is the same as add. Okay, subtract of the negative number, same as add. TST is like AND, simply. TEQ is like EOR. EOR of identical number gives result 0. Okay, so these instructions only work on register, not on memory. Okay, syntax is like operations, conditions, S bit, and then register, RN register, and operand. The comparisons set flag only, then do not specify RD. Data movement does not specify RN. Second operand is sent to ALU via barrel shifting. This is another unique thing in ARM processor. Barrel shifting, the second operand, means here you can use barrel shifting to change the number actually. So what is barrel shift? Barrel shifter. The ARM actually does not have actual shift instructions. Instead, it has barrel shifter, which provide a mechanism to carry out shift as a part of other instructions. So what operation does the barrel shift supports? Let's see. Actually, if you have operand 1 and operand 2 will go through barrel shifter and it will get added. And if you shift this in some way, means ultimate result would be like multiplication of something, means we can use this simple addition for multiplication also. So how does it work? Means this is operand, this register optionally with shift operation. Shift value can be either be 5-bit unsigned integer is specified in bottom byte or another register, and it used for multiplication by constant actually. The immediate value 8-bit number with the range of 0 to 255, rotated right through even number of positions. It allows increased range of 32-bit constant to be loaded directly into the registers. To know more about it, let's see some different thing. Barrel shift left shift. The shift left by a specific amount, it means multiply by power of 2. For example, left shift by 5, it means you multiply it by 32 and then add it. Means if you are multiplying it by 32 and then adding it here, means if you rotate it by 5-bit, it means you are nothing but multiplying it by 32. By 30. Yeah, multiplying by 32. It works simply like LSL 5-bit rotate. It will shift the shift the 5-bit. It means it will get automatically multiplied by 32, and then it will get added. Similarly, right shift, barrel shift, right shift. Here what it will do, it will divide it by 32. So shift by the specified amount here. I think it's not visible to you. Let me do something. Yeah. The logical shift right. It means you're dividing it by 32 and then adding it with some other number. So there are two kind of logical shift. Another is like arithmetic shift. Barrel shift rotation. What is that? To rotate right means ROR. Similar to ASR, but bit wraparound as they leave the LSB and appear as the MSB. ROR 5 means 5 time rotation. So note that last bit rotate is also used as a carry out. This operation we can use to take out the carry. RRX, rotate right extended. This operation use the CPSR C flag as a 33rd bit. Rotate right by 1 bit, encoded as ROR #0. Okay. Oh, these are the thing. Means here we use barrel shifter and then just simply add it. Means using this mechanism we can do multiplication also, and then thing will be very fast. Single register data transfer is like regular stuff. LDR, load, str, store, word. Word means 32 bit wide. LDRB, SDRB means 8 bit because this is byte. LDRH, SDRH is a half word. Okay. LDRSB, signed byte load. LDRSH, signed half word load. The memory system must support all access sizes. Syntax is LDR, condition, size, RD and address, store, condition, size, RD and address. Just like LDR EQB. Cortex M3 data path. What is there here? The Cortex M3 is based on Harvard architecture. So there are separate instructions and data bus. Instruction come in along the AHB instructions. Read bus to decode the stage. HA address is the address bus on the instruction side bus. This one is the instruction side bus. This is data side bus, and this instructions decoder. So there are separate read data and write data registers and data address bus. Now the M3 is also considered to be LDSTR architecture, load store architecture. So all data processing is performed on registers, not directly on memory location. So we can say something like address R0, R1, R0, R1, R2, LS2. What does it mean? Means R1 come along both A and B bus. Second operand through barrel shifter, so we can do something like barrel shifting, and then it will add up in R1, it will go into the R0. This diagram refers what I am saying. If I let me draw somewhere in notepad. It is like add R0, R0, R1, R1, comma, then LSL #2. Means R1 come along both A and B. R1 will come along both A and B buses, and second operand through barrel shifter. So we can do something like here. Okay, because this one is coming through barrel shifter. This one it will get shifted, and then this two will get added, and then it will go inside. Okay, A operand is a B operand. B operand will undergo through barrel shifting, and then new product will come, means it's multiplied by is a #2, right? So 2 to the power 4. It's multiplied by 4. Yeah, means R1 into 4 plus R1 will go into R0, means total R1 into 5. R1 into 5. Okay, now we covered ARM architectures, programs, models, etc. Now we'll focus on system design. The overview of some of the hardware and software technology that ARM has to support the design in and of the ARM core in a real product that we'll go through, and also I will look into some of the issue involved in the memory map ARM based system. See, this is typical SoC design. This is how GPU look like in the context of full SoC. The GPU is designed and optimized for AMBA. So it supports most of the features provided by AMBA and allows easy integrations with the new AXI ready core and bus fabric. AMBA is a bus protocol. Okay, so the GPU is designed for a unified memory architecture where the single memory subsystem is shared between the main processor, means ARM 1176 here in this case, and GPU. So ARM 1176 has separate L1 and L2 instructions and data cache, and L230 here is an AXI L2 cache controller. The PL301 is here PL301. Okay, this is PL111 and then PL301 is for primary peripheral license for ARM. This is for primary peripheral license for ARM. So if you see this one, this PL301 high performance matrix, this PL301 is a primary cell peripheral licensable from ARM that provide low latencies, high bandwidth interactions in our interconnect between multiple bus masters, slaves and memory, and support all AMBA protocol, whether it's AHB, APB and AXI, whatever. You can see the connection here between the bus, interconnect and the dynamic memory controller, which is an ARM prime cell peripheral, which controls some high speed DDR memory and maybe some PHYs to connect the physical medium like Ethernet, USB cable. PHYs are physical layer of OSI model, abstract description standard of computer network protocol and comms. Okay, PHY is a physical layer. As we saw in the last slide, we have AMBA AXI, AMBA APB interface. Here our reset signal, which would be under software control of the processor, and here are the interrupt output, which are routed to system interrupt controller, which in the case is another prime cell called PL390. This one, PL390, generic interrupt controller GIC, which takes in a number of interrupts, priorities them, and signals to the core via the two interrupt FIQ, FIC and IRQ pins. So the resulting video frame is written by Mali 200 pixel processor to main memory, where it is accessed by color LCD controller and sent out to the LCD. The controller in this case is another ARM prime cell called PL111. See, this one is ARM cell, this one is ARM cell, this one is ARM cell, and this whole system. So this is typical about SoC design, where ARM product will get fit in and how it provide interface and all. The last topic of this session is development tool. I think we are running out of time. What we'll do, we'll cover this one in another video. Alright, then bye bye, see you in the next video. Bye.